I'll go through an example where we use a free body diagram to develop a net force and then apply Newton's second law of motion to determine what the acceleration is given that net force. So this is a case of three astronauts are pushing with their jetpacks on an asteroid, trying to move it. So this is maybe a scene from the movie Armageddon. So force 1 is along the vector for F1. Second astronaut is pushing with F2, which is parallel to what I picked to be my x-axis. And then astronaut 3 is pointing with the force F3. The asteroid is not too big, 120 kilograms is its mass. Force 1, magnitude and direction relative to the x-axis. Force 2, 55 newtons along the x-axis, and then F3, 41 newtons, 60 degrees below the x-axis. First thing I want to do is just try to get a rough sense of what I think the answer should be for the acceleration. And to do that, I'm just going to graphically add these three vectors together and get a sense of where they're going to point. So I've got F2 straight to the right, F1 is mostly to the right and up a bit, and then F3 is mostly down and to the right a bit. And the vector sum of those three goes from the tail of the first vector to the head of the last vector in the sum. So I would have a net force. It's going to look something like that. So I expect the net force and therefore the acceleration to be mostly to the right and a little bit down. And that is, for my chosen coordinates, that's going to be in the fourth quadrant. So expecting an answer in Cartesian components that's positive x and negative y, or expecting an answer, if you think about it in polars, it's in the fourth quadrant. So it's an angle between 0 and minus 90, or if you're rather, between 270 and 360, to be in the fourth quadrant. All right, and then an observation that I want to make to keep this fresh in your mind: the net force has to point in the same direction as the acceleration. The mass here can't be negative. So all the inertial mass doing from a mathematical point of view is rescaling. It's like a constant proportionality between acceleration and net force. But it can't be negative, so I can't flip the direction around. All I'm doing is changing the length of vectors, so it has to be true always that the net force is parallel to the acceleration. Okay. I'm going to find the x component of the net force first, and then we'll find the y component. So the net force along the x direction, well, that's all of F2, is part of F1. It is the part of F1 that's parallel to the x-axis. So that is F1 cosine theta 1, and then it's the part of F3 that's along the x-axis. So that's plus F3 cosine theta 3. So let's put in values for that. We've got 55 newtons plus 32 newtons cosine of 30 plus 41 newtons cosine of 60. And then I get that to work out to be, just so you can check for yourself as you're going along and you have your calculator figured out, so you're in degree mode and not radians when you think you're in degrees. This works out to 27.7 newtons for the part of F1 along the x-axis, and I've got 20.5 newtons for the part of F3 that's along the x-axis. That all adds up together to be 103.2 newtons. So I'm keeping a little bit extra information. I'll go back and round to 3 digits when I'm done. Now I need to do the same thing on the y direction. F net along the y direction. Well, F2 doesn't contribute, and I have part of F1 that points up, and then part of F3 that points down. So I'm going to have an F1 sine theta 1 minus F3 sine theta 3, and fill in what those values are. (32 newtons times sine of 30 degrees, then minus 41 newtons sine of 60 degrees. Again, make sure we're all happy with our trig functions. I get that to be 16 newtons, because sine of 30 is a half, and minus 35.5 newtons. I get that to be minus 19.5 newtons. All right, so the net force as our rough graphical addition of the 3 vectors is telling us, it is mostly to the right and then down. Mostly to the right, down. All right, so now we have the net force on the left-hand side. To get the acceleration, I divide the net force by the mass, which is 120 kilograms. And then writing this out vectorially, we have an x component that is 103.2 newtons divided by 120 kilograms, and that's along the x direction. And then the y component, 19.5 newtons over 120 kilograms. That's j hat. And then just sort of finishing things off, plus 0.86 meters per second squared on the x direction, minus 0.16 meters per second squared on the y direction. And then lastly, I want to go through and convert this not into Cartesian coordinates but in magnitude and direction. So sometimes in a problem you'd be asked for a vector, and you just give me the components, hunky-dory. Sometimes you'd be asked for a magnitude and a direction. So for the magnitude, it's just the Pythagorean theorem. The x component squared plus the y component squared is the square of the hypotenuse, and x is always perpendicular to y. That's why we like Cartesian coordinates. So we've worked that out. I got that to be 0.87 meters per second squared is the magnitude And then the direction is theta is, got that to be 10.5 degrees below the x-axis. Where you have to be sort of careful with this. Conventionally, a positive angle would mean I'm making a rotation that is counterclockwise. So that would be a positive angle of 360 minus 10.5. That's sort of a mouthful, so instead I just included these words that I'm measuring this angle to be below the x-axis. Perfectly fine, as long as you are uniquely specifying what the angle is and it's not up to a guess or an interpretation. And it's not, because I provided what my axes are up there. And then this 10.5 is coming from the arctangent y component over the x component. So opposite over adjacent. And your own calculator, you should become familiar with how it works. Some people, your calculator is going to have inverse trig functions that take two arguments, like the numerator and denominator in a ratio, and that will keep track of what quadrant you're in automatically by the signs, SIG and S, of the y and x components. If you have a single argument, like inverse tangent, arctangent function, then you need to mentally think about what it is you're doing. If I'm putting in minus 0.16 divided by 0.86, you're going to need to mentally think about what quadrant that's actually landing in so you can interpret what the angle means. Short version of this is you need to think. The calculator is just not going to automatically solve all problems for you. It's a tool, but you still need to think.